Right. Question 11. A function f is defined by fx is equal to 1 over x squared minus 2x minus 3, where x is an element of real numbers and x cannot equal -1 or 3. Part A asks, sketch the curve of y equals fx, clearly indicating any asymptotes with their equations. State the coordinate of any local maximum or minimum points and any points of intersection with the coordinate axes. Okay, cool. Now let's copy this down to a new page. Oh, chop a little bit of the one off there. And now let's have a look at what we've got. So first things first, we'll start with the idea of the asymptotes. And once again, it's relatively kind that we're given the values of x, which that can't, with values of x that are not applicable to fx, or we cannot substitute these x values into fx, because essentially what they will do is make our denominator equal to 0, and we can't divide by 0. And I said before in an earlier question that these essentially just give you the equation of the vertical asymptotes, right? So in fact, let's highlight our information. So we got asymptotes with their equations. We got coordinates of any local maximum or minimum points, and points of intersection with the coordinate axes. All right, so we'll go through these three things first, and then we'll get to sketching the graph of y equals fx. Okay, so let's first of all, we can put in vertical, and we'll put in a little a here. Okay. Vertical asymptotes are going to be x is equal to -1 and x is equal to 3. All right, so that's a nice one there. Moving on to the horizontal asymptote. Now this is the limit as x tends to positive and negative infinity of fx. And a bit of a hard and fast rule that you can remember is that if the degree of the denominator of a rational function is greater than the degree of the numerator, which is just 1 here, then the limit as x tends to positive and negative infinity will be equal to 0. And hence then the horizontal asymptote will be y is equal to 0, or just the x-axis. Okay, it's a bit of a hard and fast rule you can remember there. So therefore, the horizontal asymptote is y is equal to 0. Okay, that's nice. Now, so maximum or minimum points, let's go on to that. So the easiest way to calculate this, in my opinion anyway, is to use the reciprocal function of f, or just identify that fx is the reciprocal function of x squared minus 2x minus 3. Okay, so if we just said, let's use g, let's say gx is equal to x squared minus 2x minus 3. Okay, and what we could do is we could factorize this here, and we could say that this is equal to x plus 1 multiplied by x minus 3. Right, and we can see here that if we lob in x is equal to -1 into here, that will make the equation equal to 0. And equally, if we put in x is equal to 3 into this equation here, it'll make it equal to 0, which will mean then the graph of f will be 1 divided by 0, which we can't do, so that's why it's a vertical asymptote. Yeah, we've talked about that. So then the graph of g will have a minimum point, since it's a positive quadratic. Okay, so g min, or the minimum point of gx, will be the x value that is directly in between -1 and 3. Okay, and that's x is equal to 1. All right, and so now if we lob that into our function, and we'll get rid of the underline there, we're going to get 1 plus 1 multiplied by 1 minus 3. And that's going to equal 2 multiplied by negative 2, which equals 4. Okay, so then that means negative 4. Negative 4. It's equal to negative 4, which means then, therefore, the minimum, G min, is at 1 comma negative 4. Right. Now, a relationship between reciprocal functions that you can use here is that the graph of f, since the graph of g has a minimum point, that means the graph of f will have a maximum point because they're reciprocal functions, and the x value will be the same for both these 2 points. So for the minimum for the graph of g and the maximum for the graph of f. So we can say, we can go through and say, therefore, f max will be when x is equal to 1. And then the y-coordinate will just be the reciprocal of the y-coordinate in for g. Okay, so you can sort of visualize that, because if we put x is equal to 1 into f of x, we'll see that we get 1 over essentially negative 4, because we know what happens when we put it into that. We found that there. And so the answer here, or the y-coordinate for the maximum point of f, will be negative 1/4. All right, and so then now we have the maximum point and we've got our asymptotes. Now let's look at the intercepts with the coordinate axes. Okay, so the x-intercept, so the y-intercept will always be when x is equal to 0. So we can say, let's put that y-int. In fact, I'm going to put this into blue. Let's say y-intercept is when x is equal to 0. So y-intercept is going to be f of 0, which we will see is 1 over, let's do the whole thing, 0 squared minus 2 lots of 0 minus 3. And we can see that this is just going to come out to be negative 1/3. All right, so therefore the y-intercept is 0 comma negative 1/3. All right, and then now the x-intercept is when fx is equal to 0. And we'll see from our function here, so if we lob in, so f of x is equal to 1 over x squared minus 2x minus 3. Now, there are no x values that will make this equal to 0. So this can't equal 0. So therefore, no x-intercepts. So there aren't any x-intercepts. Equally, you could have got that from the idea that the horizontal asymptote is y equals 0, which is the x-axis. It's the x-axis, and that would have been equally a fine justification. Okay, so now we've got all the bits and pieces that we need. We've got the the intercepts, or the intercept, I should say, the y-intercept, the maximum point, and the asymptotes. Let's actually, why don't we just go through and we'll highlight what we need here. So we've got that guy, got this one, got the maximum point there, and we have the y-intercept. Okay, so now if we go down to, let's create a set of coordinate axes, and we'll graph our function. We'll have a sketch of our function. Okay, so first things first, let's put in the vertical asymptote. So let's put that in there. Let's say that's the one for x is equal to negative 1. Let's do a dotted line for this. So we'll go there, and actually let's bring this whole thing down slightly. Okay, and we'll label this y x. Okay, and that is x is equal to negative 1. And also we're going to need to put in when x is equal to 3. Let's try and get this roughly right. Yeah, let's say there. And we're going to need our graph to go a bit further. No, don't want that. We just want this to come shoot off a bit there. Okay, cool. And then that's when x is equal to 3, this line here. All right, nice. And we don't need to draw the the horizontal asymptote, that is just the x-axis. All right, cool. And let's put little arrows on the end here. Okay, so there are a few ways you can go about sort of finding the shape here. I would recommend, how about we put in the y-intercept first. So let's put the y-intercept, which we found was when x is equal to 0 and y is equal to negative 1/3. So let's say roughly that can be there. And we'll note that in. We'll put 0, negative 1/3. Okay, and then how about we move that to the, put that there. And then also we had the idea that when the maximum of the graph of f is when x is equal to 1 and the y coordinate is negative 1/4. So let's say that is going to be roughly around here. Okay, and we can lob that in. I'm going to zoom in actually to make my life slightly easier. Let's just put this underneath here. 1, negative 1/4. Okay, cool. So there we have a couple of points that we can use. And then now to get the shape of our curve. Well, we know that the horizontal asymptote is the x-axis. Okay, so that means we're going to have essentially flat lines along here. All right, and x is equal to negative 1 is a vertical asymptote, and x is equal to 3 is a vertical asymptote. So we're going to have vertical lines running along them. So, but that means if I have a horizontal asymptote here and then a vertical asymptote there, that's roughly going to be the shape on the left-hand side for when x is less than negative 1, because I'm sort of showing that there is an asymptote at the x-axis and a vertical asymptote of x equal negative 1. We can show that on the other side as well. All right, and so that's going to be like that. And then now for, in the middle, we have, basically our y-intercept and our maximum. So we know we're going to have to run through there, and we have our two vertical asymptotes. Okay, so we're going to need our lines to be running along there. So we essentially sort of have a line here, and a line going through there. And so it's not too hard to then, sort of then assume that the shape of this graph in the middle will be like this. Forgive my poor drawing, but that will be the graph of f, right? And that, satisfies everything that we need. And we have, we can also, then we might also just put in down the bottom here, horizontal asymptote. Let's write that underneath. Of y is equal to 0. And then, there you have the answer to question 11a. Okay, on to part B. So we have a function g is defined by gx is equal to 1 over x squared minus 2x minus 3, where x is an element of real numbers and x is greater than 3. Part B says the inverse of g is g to the power of negative 1. Okay, and part 1 of part B is show that the inverse of g of x is equal to 1 plus the square root of 4x squared plus x all over x. And part 2 says state the domain of the inverse of g. All right, so let's copy this question. Oh, what have I done? Let's copy this question down to a new page and look at what we've got. Okay. So it's worth noting that g of x is identical to f of x, but the only thing we've changed is the domain. All right. So basically for x is greater than 3. Okay. And so if we go back up to our graph and we take that here, let's copy this down. Let's just visualize the bit that we're going to be working with. Okay. So the bit of the graph that we're going to need to consider is essentially just this bit here. Okay. So the part that is greater than 3. All right, and so now, in order to find an expression for the inverse, what we tend to do is say, let y equal our function, so g of x. This just makes it easier to rearrange in the following steps. So we can say then y is equal to 1 over x squared minus 2x minus 3. Okay, and then what we actually also what I'm going to note at the same time is the domain and range. Okay, so this is for x is greater than 3, and we can see from our graph up here that when x is greater than 3, then the graph of g is always greater than 0. So that means y is greater than 0 as well. Okay, and so now we swap our x and y's. All right, and so we get x is equal to 1 over y squared minus 2y minus 3. And then now a domain and range have changed. So this is for x is greater than 0 and y is greater than 3. And now we just go about sort of rearranging this equation for y. I'm going to bring the y's over to the left-hand side because generally that's how we write equations. We're going to put y is equal to something. So I'm going to say y squared minus 2y minus 3 is equal to 1 over x. If you're familiar with physics triangles, that's an easy way to rearrange that one there. All right. But yeah, so that's what we've got there. Now, what we can do to this left-hand side is we've got to start making our equation start looking like this. All right. And so the best way to do that is to complete the square on this left-hand side where we've got the y's. Right. And the way we do that is we think, what would we need to put into brackets and square to get this bit here, to get y squared minus 2y, right? Regardless of what's going to come after that, the constant at the end, we're going to basically account for by subtracting it off of the end as well, okay? So that's going to be y minus 1, all right? And you'll see if you square that out, you times this bracket by itself, you'll get y squared minus 2y, but then you'll get plus 1 on the end, okay? And the way we account for that plus 1 on the end is we just subtract, just subtract 1. Yeah, there we go. Subtract 1 minus 3, and then the minus 3 is from that bit there, okay, is equal to 1 over x. We can clean this up a bit and say that this is just y minus 1 squared minus 4 is equal to 1 over x. Now, the next step will be to add 4 to either side, but so that we start getting an expression similar to what we've got here, right, I'm going to put the 4 in front of the 1 over x, all right? It'll make sense in the following steps as to why I did that. So we're going to get y minus 1 squared is equal to 4 plus 1 over x. Okay, now if we essentially now just multiply our right-hand side by x over, just get a similar denominator, get the same denominator on our right-hand side, we can change this to being y minus 1 is equal to 4x squared plus let's say over x squared plus x over x squared. Yeah, we'll do it like that. Okay, and then we can, I forgot the squared here. Then we can say that this is y minus 1 squared is equal to 4x squared plus x over x squared. Now we're going to take the square root of both sides, and that's going to give us y minus 1 on the left-hand side is equal to plus and minus the square root of this whole thing. Okay, so x squared plus x over x squared. Now, when you take the square root of a fraction, I'm just going to clean up this side bit here. So when you take the square root of a fraction, it's equal to the square root of the numerator over the square root of the denominator. All right, so, and the square root of the denominator here of x squared is just going to be x. And yeah, all the thing that is guiding all of my actions here is the fact that I'm trying to work towards this expression here. Okay, and so I can see that this bit here, that's what I'm trying to get to here. All right, so then I can say y minus 1 is equal to, in fact, how about we'll add 1, oh no, we'll do 2 steps here. We'll do 2 steps. So this is equal to the square root of 4x squared plus x over x. Now let's work off to the right here, and what we're going to do is draw a margin, and we'll bring this over, and we'll just copy the same step up to the top here. Okay, and so now what I'm going to do is add 1 to both sides, and same idea, I'm going to put the 1 in front, like I did with the 4, so that I get an expression similar to what we have in the question. So we're going to get y is equal to 1 plus and minus the square root, or how about we just copy this down, eh? And since at the start we said that y has to be greater than 3 and x is greater than 0, so let's write that in. Since x is greater than 0 and y is greater than 3, that means we're going to have to reject this negative sign. All right, we're going to have to reject the idea that, because if we had that, then essentially, and knowing that x is greater than 0, that means this whole expression here would give a value of y that is less than 3, which is not allowed. All right, so we're going to have to say then, therefore, y is equal to 1 plus the square root of 4x squared plus x over x. Okay, and that's essentially what we were going for. Now we just need to swap out y and g, or the inverse of g. All right, and we can send there, therefore, g of -1 x is equal to 1 plus square root of 4x squared plus x over x. Okay, on to part 2. Part 2 asks, state the domain of the inverse of g. Okay, so domain of the inverse of a function is equal to the range of that function. So the range of gx is equal to the domain of the inverse of gx. Okay, and so we somewhat sort of noted that here. So that was the range of gx, and so that means the domain of gx is, or the inverse of gx is here, which is x is greater than 0. Okay, so we can note that down here. And we'll say part 2. Okay, domain of g inverse is x is greater than 0. All right, and that is the answer to part 2. We'll put x here. Right, there we go. Okay, on to part C. We have a function h is defined by hx is equal to arctan of x over 2, where x is an element of real numbers. Given that hog of a, or h of g of a is equal to pi over 4, find the value of a. Give your answer in the form p plus q over 2 multiplied by the square root of r, where p, q, and r are elements of positive integers. Okay, tricky one, but we'll what we'll do is we'll take our function g, including its domain. Let's sub that down here. Let's just sort of like make it a bit smaller. All right, and then we'll copy this down to a new page. Copy, let's go down to here, add page. Okay, cool. And so here we have our function. Okay, so first things first, I reckon a good idea would be to get an expression for h of g of a, or log of a if you, or sorry, of x. So h of g of x. So if we go through and we find that, let's go. So h of g of x. Okay. Now this is going to be essentially just where we substitute in the function of g as our x term into our function of h. All right. So that's going to look a little like this. So that's going to equal arc tan of 1 over x squared minus 2x minus 3, and that's all over 2. All right, and then we can clean this up a little bit. And, oh, what have I done? We've got, that's all right. Yeah, we can get rid of that. We can go like that. All right, cool. So we can clean this up a bit and call it arctan of 1 over 2 multiplied by the denominator, so x squared minus 2x minus 3. Cool, and then now we have an expression for essentially whole of x, or h of g of x. All right, we know that h of g of a is equal to pi over 4. All right, so now let's show that. So we can go h of g of a is going to equal arctan of 1 over 2 lots of a squared minus 2a minus 3. Cool, and then close bracket. All right, and we know that this is equal to pi over 4. All right, so now if we go to our, let's bring in one of the exact value triangles, one with pi over 4, and we can see here that, in fact, we'll write it over here. We can see that tan over 4, or tan of pi over 4, let's just make this slightly thinner, rewrite that. So let's just say tan of pi over 4 is going to equal 1. Okay, so then that basically means, therefore, arctan of 1 will equal pi over 4. All right, so therefore we can sort of use that information there and say that our expression in here, this expression here, that's going to have to equal 1. All right, so let's put a green underline and we'll say this is going to have to equal 1. All right, and we'll bring that down. So we'll say, therefore, 1 over 2 multiplied by a squared minus 2a minus 3 is going to have to equal 1. Now we'll bring the 1 over to the other side. And so we're going to say that 2 multiplied by a squared minus 2a minus 3 is going to essentially equal 1 over 1, which will just be 1. All right, and then now we can, let's make this equation equal to 0. So then we will have a quadratic equation. And so we're going to get 2a squared minus 4a minus 6, and then also minus 1, because we're going to bring that over to the other side. So it's going to be minus 7 is equal to 0. And then now, yeah, we have a quadratic equation where we can use the quadratic formula, which is as follows. We'll bring this over here. So quadratic formula is x is equal to negative b plus and minus the square root of b squared minus 4ac over 2a, where b is the coefficient of the h to the power 1 term, or a to the power of 1 term in our example here. A is the coefficient of the x squared term, and c is the constant on the end. So we can do that. So we've got a is equal to negative 4, which is just going to be 4. Okay, plus and minus the square root of negative 4 squared, which is essentially just the same as 4 squared, but I'll write it in, minus 4 times by a, which is 2, times by c, which is negative 7. All right, cool. And then that's all divided by 2 lots of a, which is 2 times 2. All right, cool. Now we can clean this up a bit. And so let's go ahead and do that. We'll say 4 plus and minus the square root of 16. This is going to end up being plus 56, I believe. Yeah, 56. 6. Okay, all over 4. And then we can also clean this up a bit. What we'll do is we'll draw a margin down here, and we'll work off to the right-hand side here. Okay, and we'll copy the same step. All right, and so we have a value of 16 plus 56, which will give me 72. And so I can call this here. Yep, a is equal to 4 plus and minus the square root of 72 all over 4. And now what we can do is separate this into 2 separate fractions, if you will. So we could say we'd get 4 over 4 plus and minus the square root of 72 over 4. Now, 4 over 4 is just going to be 1. So we can say a is equal to 1 plus and minus the square root of 72 over 4. Now we can basically break down the square root of 72 by thinking of its squared factors, I like to call it. So basically numbers that go into 72. So the first one that comes to mind is 36. So 36 is 6 squared. So, and 36 times 2 is 72. So in fact, let me just write that in. There's going to be 1 plus and minus the square root of 36 times 2 over 4. Okay, so that's going to be the same as writing 1 plus and minus 6 root 2 over 4. And we can simplify the 4 and the 6 to be 3 and 2. Divide them both by 2. And so we get 1 plus and minus the square root of, 3 multiplied by the square root of 2 over 2. Now, we might be wondering now, how do we find the value of a? And we have to go up again and see that we had g of x was part of our function here. And g of x is only valid for values of x that are greater than 3. Okay, so therefore, that means a has to be greater than 3. And so therefore, a must be greater than 3. And so if we're starting with 1 and then subtracting something, we could never be greater than 3. So we have to basically take the positive version of the right-hand side. So therefore, a is greater than 3. And so a is equal to 1 plus 3 over 2 multiplied by the square root of 2. And that is the answer to part C.